it's been pretty amazing to be kind of at the forefront, at the cutting edge, to see all the luminaries in the field, and you find out that these big names are just people with a lot of common interests that overlap with yours, and who will only be too happy to talk with you about them.
What's the deal with that pandemic, huh? I want to get it out of the way. Anybody doing remote work during the pandemic? Remote work remotely? Thank you, thank you. Anybody has done, anybody has been like to high school and or college? A lot of homeschooling, good, awesome. So anybody has been in an event in high school, they're not supposed to be late, but they've been late. Like that dreaded feeling, like, you know, there's a play you're supposed to be in, there's a soccer game, there's a basketball game, there's an exam, you know, there's something you're supposed to be in, and you're like 15 minutes late, or half an hour late. And you have that dreadful feeling. Like, you know, you go and you're on the soccer field, like, man, you're late, we're 2 goals down, you get your shoes, quick, hurry, warm up. Don't warm up, just get in the field. That's, you know that feeling? That's remote work for me. This is remote work. Because every morning I work with this company in London. So every morning I wake up, make a coffee, I get, you know, I sit down, and everybody's in the middle of the day. It's like 2 p.m. there. So you're like, oh man, oh, you're late. What are you doing? Your bug. We're fixing your bug right now. The machines are burning. Like, it's terrible what's happening. Where were you? Well, I was sleeping, right? And then there's like folks in Singapore, they're like, oh, I'm going to sleep now. It's like 10 p.m. by my place right now, right? And there's folks in Vancouver who like didn't wake up yet, right? So that's pretty terrible. And you know, the funny thing is, this whole thing is, the next day is the same. Like, it's like, you know, it's like Groundhog Day. I wake up the next day, it's like, oh man, again, I'm late again. All right, so fine. So it's 9 a.m., I'm getting in shape, everything. I load the code in my mind, and all good. And then like, I'm ready to work now. And what happens next? Everybody in London is leaving home. Like, yeah, so I'm gonna have a whiskey with me dad, me father, right? So pardon my British accent, I know it's like horrible. So it's like, it's a terrible feeling every day. So I'm sure you can relate to that if you've done any remote work with a global company. But that has nothing to do with embracing and also destroying variant types safely. Now the safely bit is important, because John Lake has told me he's gonna buy me a beer every time I use that word. So with luck, by the end of like tonight, I'll be an alcoholic. All right? So there's been a bit of discussion about this book coming at the end of the year. It's available for pre-order on Amazon. And there's an interesting history to this book. So John and Vittorio Romeo started it. They both have or have had talks at this conference. And I kind of, I was collaborating with John a bit. And I had the passers-by interest, a polite interest, like, that's a nice book. It's a good idea. It's kind of a cool concept. And then, before long, like, John kind of got me into his maelstrom. So he got me into this whirlwind of interest and stuff, and I ended up writing a whole chapter. And this talk is in part about that chapter. So I ended up writing the whole chapter on variadic templates. So, let's get the sponsorship out of the way. But I'm also a hardworking father of 2, so I got 2 jobs. All right? That's the London company. So our plan today is the following. First, we're going to discuss a bit about variadic templates in general. I know I'm preaching to the choir, so there's good motivation and everything that we're going to recap essentially. But I'm going to discuss a couple of rules that are not obvious when you do when you figure out what the variadic template is supposed to do. Then we're going to discuss variant types and why do we care, why they're important to us. And last but not least, we're going to discuss the converse factory method pattern, which is a very well-known term that I just made up. And it's going to be something that's interesting because it's the opposite of the factory method pattern. The factory method pattern, you don't know what you're creating, right? But you know what you're destroying. But with variant, it's kind of the opposite. You know what you're creating, but you have no idea what you're destroying, and that makes it difficult. So let's see. Variadics. What's the deal with variadics? So there's a lot of pressure, if you wish, on functions that can take a variadic number of arguments, and class templates that can take a variadic number of arguments. And the solutions extant in C++03 were pretty bad. Think boost tuple. It was like it is limited and very bulky in implementation. I think it accepts up to 20 template parameters, and that makes it quite limited, and also kind of unpleasant to write, debug, maintain, and use. So with variadics, we have the opportunity to actually create simple function and class templates with arbitrary numbers of arguments, no limitations. A nice application are the algebraic types, tuple and variant, which are in the C++ standard, added different times, so C++11 and 14. Efficiency, whenever you do something like you want to concatenate a number of strings, which is a very common thing to do when for example, you're assembling a web page, or you're assembling a response string for a server. It's very common that you want to assemble a number of strings that come from different places, and you want to do that efficiently, obviously. The simple solution would be to concatenate in a cascading manner, and that would mean there's a lot of copying and allocation along the way. Whereas if you define a function concat that simply takes a variadic number of strings by constant reference, also characters, also const star, whatever you have, you're going to have the opportunity to pre-compute the length once, allocate memory once, and copy only once into the destination. So that's very nice. It goes a lot with, of course, mathematical calculations, such as, you do algebraic manipulation, matrices, vectors, and so on. If you want to do cascaded operations, it's much more efficient to do them in a variadic. Now, locking considerations are also a thing. Like, one of the nice things about printf is that it only locks the stream once, as opposed to cout, which locks it at every step, right, along the way. So that's a nice thing. Whenever you want to print something, you assemble the thing, you lock the stream, and then you print everything in unlock. And with a variadic, it's very natural to do it that way. There would be an application that may seem less obvious, which is you want to forward to constructors that you don't know the arity of. And that's these two make unique and make shared and in place form examples of this pattern. So essentially in these functions, you want to create a constructor in a generic manner, but you have no idea how many arguments that constructor is supposed to take. So you need a way to kind of take any number of arguments, accommodate any constructor, pass them into your function, and your function is going to later call the constructor. So all of these are enabled by variadics. And it doesn't stop here. Variadics open new opportunities. So consider the standard functions. I just took a minute to browse the standard a bit, to look for a few algorithms. All of, any of, mismatch, equal, merge, set union, and set intersect, all set operations could and should be variadic. Now what's the advantage? Consider a function equal. Equal right now takes two ranges. 4 iterators, right? 2 ranges. But what if I want to compare 3 arrays? And I want to make a decision if all 3 are equal, right? One solution would be to compare the first with the second. And if that goes through, if that returns true, then compare one of them with the third. What am I wasting here? I'm wasting a huge opportunity because maybe I have 2 arrays that have 1 million elements each, and the third has like 1 element, right? So what you need to do if you want to compare in a smart fashion multiple arrays, you want to do it vertically. You want to compare the first elements of all arrays and the second elements of all arrays and so on. That may be slower if you have 2 or 3 or 4 arrays and they're all short. But this is a decision you need to be able to make, right? And interestingly enough, so all of these functions can benefit greatly. In fact, set intersection with multiple inputs is pretty much how Google works. So they have a variable number of inputs, but essentially set intersection with multiple sets is a fundamental operation in a variety of retrieval tasks that are very important to the functioning of queries and AI and stuff like that. So I very strongly suggest that you consider contributing things like variadic equal and merge and set operations to the standard. By the way, you're going to have a huge difficulty implementing such, because when you need to iterate vertically, and that's very unusual for variadics. It's not the thing that variadics do. Variadics very much favor cascading things, such as I want to compare the first with the second and the second with the third array, but they don't allow things like I'm going to iterate vertically through the 3 arrays or 5 arrays or whatever in a loop. There's no such loop. You would need static 4 for that. I'm not kidding, actually. Remember I had this pet peeve, static if? Now here's the second, static 4. So you're going to need that. Otherwise, it's going to be hundreds of lines of code that are pretty difficult to go through. So variadics are kind of a difficult topic. I thought I understood it until I had to write it for the book. And I realized there's many levels of nirvana in understanding variadics. So the rules are, it's just like there's a lot of deus ex machina, and there's a lot of hand of God in the way the rules are written. It's just, and here we're going to do this, and if that happens, you're going to do this. So it's a lot of rules, exceptions to exceptions, and so on, recursively. So that's a bit of a problem when learning about variadics. They interact, of course, with the rest of C++, and that's actually what forced people from defining all of those rules and exceptions and a variety of by fiat dictums. You must memorize, there's no way around it, I tried. There's no way around it. You must memorize what expansions are allowed, and you must memorize where expansions are allowed. And there's no way that, there's no shortcuts that can help with that. You just have to have a list handy. So whenever you program with variadics, you gotta have like a second monitor there with the list, right? The deduction rules, however, they are not listed anywhere. They're they're in the standard, but they're like 15 places in the standard. So you gotta read like this and that, and you have to turn it upside down sometimes, believe me. And only then you kind of figure out how deduction works for templates. When I say deduction, whenever you have variadic function templates and you have a call, you gotta figure out how template parameters are deduced from the actual arguments. So those are like absolutely crazy difficult. I'm talking like Turing complete. I'm not kidding. Actually, the standard at some point is going to say, you're going to see it. At some point, the standard is going to say, you know what? This is illegal, but we can't prove it. I'm not kidding. It's coming. So the most important thing to understand about variadics and what should motivate your entire approach to understanding them should be that packs are a distinct kind. Kind is a term that comes from theoretical computer science, programming languages theory, and Haskell uses it. In Haskell, all types belong to the same kind. And then you have some mechanisms to map types to types. That would be a function from kind to kind. So you have a function that maps you one kind to another. And that's it. In Haskell, there's only these 2 kinds that you have. In C++, all types belong to the same kind. But as Lior told me that Walter Brown told him, it turns out that in C++, if you look closely, there are 14 kinds. Pointers, arrays, references, integrals, it's a floating point. So, if you enumerate them, there are 14. But you should know, they're like, in 1998, they're like 12. So this is not, you don't lightly add a new kind. The only new kinds that were added by C++ with starting with 11 were, who knows? Louder, Marshall, gotta be louder. Yes, 2, another one. I have a more interesting one actually. Thank you, null pointer type. That's its own kind, right? And interestingly enough, template names are another kind. You can't do with a template name what you do with a type, right? A template is in a way a function that takes a type to another type because you instantiate with a type or more or whatever, and it brings you new types. So those would be equivalent to Haskell's mapping thing. So there is a one-of-a-kind construct that does not have any kind. Who actually does have a kind, but it's unique and it's not named anywhere, and you can't take the type of it. What is that? There is one operator in C++ that yields you something that you can't take the type of. There is one, go through the list. There is one operator in C++, there are two operators in C++ that yield something that you cannot take the type of. It's its own kind. Namespace, no. Huh? Type ID, no, it returns a type info. Thank you. But, getting interesting. Yes? Other thoughts? Sorry? Lambdas? No, they have types. They are not named. They are Voldemort types. That's a different thing. Sorry? Who said that? Who said that thing? Okay, you gotta say it louder. Address of, yes, thank you very much. So, by the way, the person who just answered is the only person in recent memory since like 10 years ago who wrote his own compiler for C++, so he should know, right? All right, so pointer to member function, pointer to object, arrow star, pointer to member function, that yields something that you can't take the type of. It's its own type. It's its own kind. You can't take that. You can't take the type of that. The only thing you can is actually put that thing in a parenthesis and apply the parenthesis operator to that. So now picture this. You're at a party. You're having a good time, right? What a great icebreaker. Nice shoes. Do you know what operator has no type? That's pretty awesome. Everyone's gonna love you. All right. So adding new kinds is almost unprecedented. Like in 20 years they added like 2. Yet all of these packs are their own kind. They add a whole different kind. So that means you should forget everything you know about values, types, templates, everything when you learn Verdict templates. So consequently, the number 2 thing to understand that's important when dealing with Verdict templates is that there's only 2 things you can do with a pack. And both are confusingly enough introduced by ... which in itself is confusing enough because it's that's a literary device more than punctuation, but anyway. So it's all about ... It's all about the suspense, right? All about uncertainty, like ... right? So whenever I have a ... to the left of a name, it means I'm introducing this name. As in template type name, ... tis. So whenever the ... is followed by a name that was not previously there, it means you're introducing a new name. It's not a precise definition, but it's a good mnemonic. Whenever I have a ... to the right of something that looks like a type or an expression, that looks like an AST piece, that means expand the stuff. And believe me, there's nothing else you can do with the pack. Literally, there's nothing, you can't give it a different name. There's nothing else you can do. Absolutely. So you can introduce them and expand them. That's it. That means out the door are all of the computer science you've learned, all of the programming experience you've had, everything is out the door. That's a huge bummer. I can't tell you just how bad this is because you gotta learn a whole new, different, and very limited, as it turns out, way of doing things. Right? I'm going to open a parenthesis right here because there is a way out of this mess. Friends, there is a way out. Add this one line to the standard. Because if you don't, everybody's gonna add their own line. Everybody's gonna do it differently. Everybody's gonna use like tuple or variant in ways they're not in. I'm seeing nods, thank you very much. I'm seeing nods. everybody's gonna do it a different way. It should be in the standard, the darn line of code. It should be there. Why? Because it gives a pack legitimacy in the form of a type. Once you say type sequence of that nonsense, oh yes, I know what that is, it's a type. And I can manipulate it with all of the wealth of techniques that I have accumulated in my long career as a programmer in C++. Yes? Makes sense? One line. And also there is precedent because there is such a thing which is called integer underscore sequence in the standard. There is such a thing, which by the way is the least visionary name ever, because it's not an integer sequence, it's a value sequence. Because look at that thing, last line. I mean, come on. Right? You can make an integer sequence of not only integrals, but also pointers to functions, pointers to methods, addresses of anything, and since C++20, you can do things like doubles and floats and user-defined types, and all of those are going to fit into an integer sequence. That name should be deprecated. It should be kept as an alias somewhere, like in a macro. And we should have value sequence, which is the right way. And of course, once you have a value sequence and you understand that this is kind of, well, values are a kind, types are a different kind. Oh, wait a second, we should have a type sequence. And once you have a type sequence, you're almost there. By the way, I should tell you this. Do you know direct basis in TR2? Who knows about direct basis? It's a nice introspection primitive that for any class you give it, it's going to give you a list of its base classes. Wow, that's a very powerful introspection primitive. It allows me to do a lot of stuff during compilation about figuring out what a type can and can't do. So direct basis is going to return a list of types. Can I return a pack? No, because remember, packs can't do that. You can't give an alternate name to a pack. You can't return it from anywhere. It's not first class, right? So then what do we do? What do they do? Do you know what they do? Who knows what, you're engineers, what would you do? They return something that is called underscore underscore something. I even forgot, what is it? What was it? What's the name? Reflection type list. Underscore underscore reflection type list. And you know, by the time I'm writing something that starts with 2 underscores in my code, believe me, I feel like on the piratebay.org, okay? It's almost illegal, right? You shouldn't do things with underscore underscore right in the front. You shouldn't be doing that. It's not illegal. I'm feeling dirty, right? You don't want to do that. But they had to figure out a solution, so what did they do? They invented a new type that gives legitimacy to the pack. So, yeah, we should have type sequence. And now that we have type sequence, if I get a foot in the door, I would like to have 3 more things. But, you know, you're laughing, but, you know, I laugh last because I'll be the last to get the joke. Here's the thing. You need 3 things to construct an arbitrary data structure. And we know that from Lisp. The 3 things are, give me the first element, give me the rest of the elements, and the third is? Huh? Cons. Thank you, Pablo. Cons. Create a new list from an element and another list. So, how difficult could it be? We're talking about a few lines. And we have everything. So, I'm saying these lines are the bootstrap that's going to get you to anywhere. It's been proven that that's all you need to create arbitrary data structures. So, head, give me the first element. Template of type name T, type names whatever. I'm going to have a type sequence and I'm going to return the first element. Fine. So far, so good, and I'm going to use the head, the using whatever trick that everybody does. And then we have, the ability to get the first element in any of these type sequences. Tail is easy as well, but it's something that you cannot do with packs, because with this thing, if I wanted to return a pack here, I couldn't, because you can't give a pack an alternate name. You cannot give a pack an alternate name. You can only expand it. So you can't have a meta function return something that is a pack. But you can have a meta function trivially return a type sequence of a pack. And all of the information is there, ready, and you have it. So I have the primitive. And cons is also trivial. I just write it. And then I have these three primitives, head, tail, and cons, in list like car, coulda, and cons, right? So I have the ability to create arbitrarily complex data structures and algorithms using these three primitives. I can't stress how important this is. Without them, without these three, people trying to use parameter packs for metaprogramming are in the desert, are out in the desert, lost. I've been seeing some gruesome code that tries to do things with packs, and it's just like out there in the desert. Isn't 40 years enough, my friends? Isn't 40 years enough, right? So I close the parentheses here, because actually that has nothing to do with my talk. Okay. All right, so about getting back to function parameter deduction. It's kind of interesting. I applied, so I read the whole thing in the standard. I checked with a number of folks. And then I figured there's two rules about template parameter matching in function calls that are easy and simple to understand. But they're nowhere in the standard. They're in a way deduced. So rule number one is rule of greedy matching. There's two. Rule of greedy matching says like this. Once a template parameter pack starts matching, it can't stop. There's no way to say, oh, I'm going to match this template parameter up to here, and after that I'm going to match something else. Once it starts going, it's never going to stop. The consequence of that is that, for example, it allows you to analyze functions that are relatively complex. Like this. If you have another parameter following a template parameter pack, the sheer consequence of that rule, it means that that parameter is always deduced. So looking at here, so we have a type name T, we have a pack T's, and that means U must be always deduced. There's no way to explicitly specify U. And that's going to reduce your search space when you figure out what the hell that means. It's going to reduce it considerably, right? So this is pretty awesome. So in the call, for example, f of 1 and 2, I know that U must be deduced. So U will be deduced as integer because it's the second thing here. And the first is going to be T, and T is going to be the empty list. Greedy matching. U must be deduced, period. Now when I start specifying arguments, I'm going to say f of int and int. And then I'm going to have 1, 2, and 3. I know U must be deduced, so the last parameter is taken, is spoken for. So this 3 goes to U. And then I'm going to have another one in the beginning which goes to T, and everything in the middle goes to T's. So 2 would be of type int, and the pack T's will have exactly int. Now if I specify more of them, I'm going to have int double, and again U takes cons car star, and then T's is going to take what's left, 2 and 3. So that allows us to explain easily and figure out easily and quickly how deduction works for many functions. So don't forget, greedy matching. Once a parameter pack starts matching, it's going to match everything. The consequence of that is if you have anything following a variadic, such as a pack, such as T's, such as U here, then you know it's going to be always deduced. So question, what does this do? I'm not going to spend time kind of asking everybody and giving you all the response and everything, but I'll tell you what, here's the thing. There's no way to deduce T, because I'm not taking it, there's no way to deduce it from the arguments, right? Because it doesn't take a T. So this type name here has a very boring life. It can only be int. Case solved, right? So we solve easily a number of problems like that. So actually that function arguably is kind of a little bug, because it should be easily written as a template taking only the pack and returning int. The second rule that I'm going to tell you today about is the rule of fair matching, which is in a way kind of limits the matching propensity of template arguments. A function parameter pack that is not at the end of a function parameter list can never have its pack deduced. So it's kind of the converse, but they don't compete, because one applies to template parameters, the other applies to function arguments. So it can never have. So let's take a look at an example here. So we have a function that takes a pack followed by a value, right? So that means that T's must be always explicit. There's no way for T's to be deduced. So that means whenever you have a function without a specified number of specified template arguments, this is going to be the empty list, period. There's no discussion. When I start specifying them, then I'm going to have the usual rules applying, and I'm going to match these to int double, etc. So now there's an interesting consequence to this fair matching, which goes to more complicated calls like this. Believe me, this is in a standard. It's explained in like 5 places in the standard. It's very difficult to figure. And I kind of sat down with Nina Rons and kind of made sure I checked everything with her and everything. And in the end, it's like, yeah, we have like a good rule here. So this is an interesting explanation for what happens there, because what happens is right to left matching. You're gonna see that whenever you call this function, it's gonna do some weird left to right, right to left matching. So let's see how that works. Because of the interaction of the true rules, use is always deduced and this is always explicit. So use, you know for sure you can't put it in the templates in the angle brackets there, and this always must be in the angle brackets. So the first call is going to take me, it's going to match only use, and this is going to be the empty list. The second call, the same, is going to have use, have 2 elements. So, you know, this is confusing to newcomers because they say, oh, this comes first, use comes second. So, you know, whenever I start calling the function, this is going to be filled first. No, it's not like that. This is going to be empty because it's always explicit. It can't be deduced. So that when I have the subsequent calls, I'm going to have, oh, wait a second. So I have int and char. Those go to this. That's it. Greedy matching. Right? And the rest go to, if any, go to use. So in this case, there's none, the third line. And in the last line, I have this goes to int and char. The int and char go to this. And there's one more, which is deduce, and use goes to const char star. And that's it. So I hope these 2 rules, which are also in the book. So the book explains everything, you know, all of the lists, the rules, all of the, you know, everything you need to memorize is in the book. I was very surprised to figure that I knew very little about how template, how variadic arguments work, and I thought I knew them. So it's kind of funny. Anyway, last but not least, I promised you the corner case from hell. We have a fine variadic function that has 2 packs followed by a regular. And if you call it every which way, so the first call is going to say, oh, okay, so 42. The first doesn't, you know, this is it's gonna have to be explicit, so it's the empty list. But then we have use and t, and it can never be explicit, so it's going to, 42 is going to go to t. T's and use are empty. The second call, it turns out that if you look at every call here, you're going to figure out that use is always empty by necessity. There is no way to either specify or deduce use. So use will be always of length 0. That's a bug, right? I mean, it sounds like, why is it there if it's always going to be of length 0? All right, so here's what the standard says. First of all, here's what GCC, MSVC, and Clang say. Yes, please.
So in the second example, where you're calling after you're saying equal to if b, if t needs to be, like, it's deduced always, wouldn't it be the last argument, and then wouldn't us be 1 because you're not being explicit, so it can't go into ts?
The question was, shouldn't this one here, right? Shouldn't that go to use? It turns out it goes to this because of the interaction of the rules.
I thought TS had to be explicit.
It turns out that you have an interaction of the greedy and fair matching at the same time, and the way they play together is that use is going to be always empty. Now, here's the interesting part about this. Clang, MSVC, and GCC all accept this code. They're very happy with it, and it just works. Now, here's what the standard says. Whenever you have a case that forces one of these packs to be always empty, that's illegal. No diagnostic required. No diagnostic. It's like we ran into this corner case. It's a very difficult problem, and we have no idea how to fix it. So no diagnostic required. You can do whatever the hell you want, right? So I'll stop here with this. Indeed, these are kind of brain puzzles, but that actually has nothing to do with my talk. So here comes what does have to do with my talk. So why do we care about variant types at all? Do we care or don't we? It turns out we do. So to recap, they're called discriminated unions, some types. They come all the way, like, those of you who are old enough, like, remember them from VBA. I can't believe I can still remember that. Like, I don't know, OLE. God. So I think that this is like the only time OLE has been pronounced in this conference, right? Or VBA and that kind of nonsense, right? So, they're all technology. They're also all technology in theory as well. So computer science calls them sometimes because they can hold any one element of a closed set of types at a point. So essentially the set of possible values is the sum of possible values in all types. So not to be confused with std any, which selects a value from an open universe of types. It can hold any value as its name says. So you can have a variant that takes a null pointer type, a string, a double, an object pointer, a bool or void star, and that's actually what JSON does. This kind of an allusion to JSON data type. It turns out that variants are everywhere. Everywhere. Databases, a colon is a variant because it can be like, a number, a string, a date, whatever databases have, the null, colon, etc., right? In spreadsheets, a cell it's a variant. It could be like a number, it could be an expression, it could be a string, it could be a date, etc., right? So there's a closed universe of possibilities, but the cell can take any of these. JSON, other data formats, protocols, text-based protocols, file formats, you name it, they have variants in them because there are values that can hold more than one type at a time. Not at a time. At a given time, they can hold any one of a set of types. In DSLs, the values of things that you have in a DSL are variants. The same goes about classic interpreters. Python, Perl, like any interpreter takes great pains with optimizing their variant data type because it's where the action goes. In compilers, an expression can be a variant. So I noticed, for example, I was browsing the LLVM codebase just now. LLVM defines a variant, and it can hold any data type in it that is in C++. Yes? Question? All right. So even in Herb's keynote, he mentioned variants 7 times, and it was a keynote. Do I need any more proof that they matter? Right? They're important. So it turns out that good implementation of these variants is crucial to performance. It's very important to implement them very carefully because exactly that's where the whole data-oriented action goes. Everything that's happening is happening in a variant. If you've done anything with an interpreter, you know that very well. It turns out that for STD variant, good destructor implementation is crucial to performance because you can optimize your way out of any kind of tight situation when you have a variant and kind of specialize it for specific types that you want to be fast for. But destructor is democracy. Like every variant is going to have a destructor. It's going to be called at the end of the scope. You can't avoid it. You see what I'm saying? You can't say, oh, you know what, I'm not going to call the destructor here because it doesn't fit my performance needs. No, it's going to be there, right? So it turns out that destructor is disproportionately important to performance because everything else you have the chance of specializing and optimizing by hand. So everything going forward in this hour, I'm going to talk about destruction, which is my favorite word. You know me, right? Destroy, right? So good destructor implementation turns out to be important. And to prove that, I took a measurement a few years ago at Facebook. This is the Facebook website, it turns out. I'm not sure if you can see the numbers much. But this is like the homepage at Facebook, which is very important, of course. And if you mess up with the inlining of one destructor, which is the variant destructor, you're going to find a drop in performance that is 0.5%. Here's the green stuff. So now, if the Facebook homepage drops in performance by 0.5%, that's a couple of millions a year in energy costs. Okay? So if you make one change, it's a minor decision. It's just not gonna mess with the inlining of that variant destructor. If you mess with that one little decision, you're going to affect the performance of a bottom line application, which does a bunch of things. I mean, there's a lot of action going on there, right? There's database querying, there's memcache, and there's all this stuff going on, right? But essentially, if you mess with this one destructor, you're gonna mess up the performance of the whole application, right? So it turns out that performance of destructors is crucial. So let's, before we get to the destructors, let's dispense with the layout, which uses my favorite keyword, Alignas. Alignas, you know, he's good friends with Legolas, right? So what that does is imposing the alignment of a specific type, or it turns out pack, to a data piece. And essentially what we're gonna do here is going to take the maximum of all sizes of the types involved. And here we're gonna use nicely the ... But you know, you see here the ... is not inside the parentheses, it's outside. It turns out both work. One is a bug. Because if you put the ... inside, you're gonna get the number of elements in the pack. And that's not what you want. You want the physical size in memory of things. So you put it outside and it's going to expand into the input of max. Since C++20, I should mention, you see this curly brace here and here? What is that? What is that? What's that curly brace? And you have a list of expressions. Initializer list, thank you. So it turns out that since C++20, std max and min, whatever, they take an initializer list and you can specify any number of arguments, and that's very nice. So we use that here, and moreover, we use it during compilation, which is sweet, and we get the maximum size of all types involved. And then I'm going to have the ddata type, which is going to be of the proper size and the proper alignment, followed by an unsigned, which is telling me which of these parameters in the pack is going to be active. So 0 would be like the first type, and 1 would be the second type, and so on. Turns out the std variant also has like a variant no type, or I forgot the name. It's a -1, cast to size t, and that means the variant could not be constructed, is in invalid state. And for example, you have a constructor that throws an exception, and the variant is put in that invalid state. Now, there are any number of games you can play with this. You can make the deactive member, you can make it instead of unsigned, you can make it like an unsigned car, like a 8-bit integer, right? That's sometimes going to improve your your size of the whole variant. And this is worth spending time on. We're not going to spend time on here, but essentially it's good to play with these things. Swap these two, ddata and deactive. You may want to look at swapping them. And essentially, these are things that the meta program can do automatically whenever you instantiate the variant to find the best packing. And that's kind of a beautiful thing in and of its own. And believe me, spending time on layout is very well worth your time. Okay? But that's all you need. You need some inert place to put the data in, and you need the current index of the type that you have there. Now, the implementation has a bunch of functions. The usual suspects, there's a bunch of constructors, there's a bunch of assignment operators, there's emplace, swap, comparison, you name it. Like they even have the spaceship there, right? Of course. There's a number of functions that query what the variant has. Give me the index of the current type. Give me, is it valued as by exception, meaning the variant is in that invalid state that I mentioned. There's no members that, does it hold this alternative? Visit this variant, we're gonna get to that a bit. Get if, etc. Most of them take constant time during runtime. And there are two that are very, very, very difficult. Visit and the destructor. Most of them can be done in such a way that is all fun at runtime. I'm gonna show you right now. I'm gonna give you an example. Here's the easy part. Get, it has many overloads, get. So it's going to take, this overload that I'm writing here is gonna take a const variant with whatever types, and it's going to return the current type, right? So now if get was called with index that does not correspond to the active member here, I'm going to throw an exception. I'm not sure, maybe this is trademarked, so maybe I shouldn't write this, right? All right, so then I'm going to say using t equals, give me the variant alternative for this particular index. And I'm going to cast the data to it because I know the right type is there. Now, of course, what's the deal with variant alternative t? So let's implement it real quick. So that's still the easy part. Variant alternative does a linear search during compilation. Give me an integer, give me a type and more types. I'm going to say variant alternative inherits variant alternative on n-1, and t is essentially chopping off the first type. When I do have a match, I'm going to have a 0 here, and I'm going to have some type here, and I'm going to simply return it. And that's my variant alternative implementation. It is a now classic recursive implementation of a meta program. Many of us have done it, right? Now the hard part, this is finally we're getting into my talk. We're starting my talk right now. So this is the hard part. I have visit and I have the destructor. The visit is like I have a dream. It's multiple dispatch. I'm not kidding you. So if you look in any implementation of visit, you're gonna see that it's like thousands of lines of code. It's absolutely amazing. There's no time to discuss that, but visit is kind of something worth looking into. But visit you don't need to call, so its efficiency is in a way not a major concern. But the destructor, you can't escape. So the destruction would be a converse factory method in which you know what you're creating during construction because you know the type that you're building, but when you're destroying, you have no idea what it's in there, so how do we destroy it? It's a weird Hotel California kind of thing, right? You can always create things, but you can't destroy them, right? Works? Huh? Okay, thank you for the nod. Thank you, Dave. Okay, so we're going to discuss the destruction here. Step 1, let's do a linear search. Okay, fine. So I'm going to have a destroy linear, and I'm going to take the index unsigned and a void star, which is my untyped data. And I'm going to have then a template overload, which takes the index searched for, the current index in the search, and the type and the more types. And I'm going to go, okay, so if n equals I means I found it, so I'm going to call the destructor by hand. And otherwise, I'm going to recurse with a larger index, continuing the search, and the same parameters, right? So I'm going to drop the t, recurse to the tail. So that would do a linear search during runtime. So I'm looking, is it 0? If so, destroy, otherwise continue. Is it 1? If so, destroy, otherwise continue. And you essentially iterate the indices of the possible values. So that would be my first implementation. Who likes linear search? What is better than linear search? Yeah, logarithmic, yeah, binary search, yes. Let's try something that is sorry, forgot to say, like, this is how you implement the actual destructor. So the destructor is going to initiate the recursion by calling destroy linear with 0 and the whole list of types. So that's fine. So we're like, who likes linear? Nobody. Who likes log? Log is better than linear, right? So let's try binary search. And this is pretty hard because it's a binary search that is partially doing compilation and partially at runtime. It's a weird thing. And I give credit to Pablo Halpern here for the implementation. So it's kind of a weird thing. It's, how do you do that? So it took me like, okay, so it took me like maybe a day. And then I sent it. It was horrible. It was like this, nobody will understand this, right? So Pablo came with a version that is way more readable. So you need to do a linear search at compilation because that's the way packs work, and the binary search at runtime. And this wall of text is what it looks like. So we have the low and the high, which are the limits of my search. Yes, that's in a traditional binary search manner. And then I have the runtime parameter n. And we have, nicely enough, two preconditions, a static one and a dynamic one. The static precondition says low must be less than high, so I'm kind of limiting myself to these to limit the number of instantiations. And then I'm going to have the runtime condition, n must fall in between. So these are, if these fail, then I have a bug somewhere. And then I'm going to do a classical binary search, except that some elements are compile time, some elements are runtime. So here I have a const expr, which is compile time, which computes the midpoint between low and high. And then I'm going to do the classical binary search, go left, go right, or I found it, right? So that's pretty nice, and to call it, I just initiate the recursion by saying destroy log with 0 and the full size of, the full number of types, and that's going to initiate my recursion, and it's going to do a binary search at runtime. And that's pretty damn nice. Who likes log? Who likes binary search? Who doesn't like indexing, right? If log is good, how about constant? Given an index, is there a way to call in constant time of function depending on the index? What data structure are you thinking of? Switch is not necessarily compile time, but yes, it's a good getting there. Come on, guys. No, is anybody who said array? Okay, a couple of you. Thank you. I didn't hear it, but array. Yes, I have an array. I index into the array. Boom. Constant time, I'm done. And it turns out it fits on a slide. This is amazing. So I define a little template function, destroy element, which does the destruction, it just destroys, and then I build an array with pointers to instantiations of that guy. So destroy compile time, destroy constant time is going to take the now known unsigned integer, which is my index, and the untyped data, and it's going to have a static array inside. And I put auto in there because pointers to functions, who does that, right? Who writes down the type of a pointer to function? You write auto, come on, right? So I initialize an array and I say it's going to be the address of destroy element instantiated with t's, and that's repeated for each type. So I leverage the ... I leverage compile time arrays, I leverage auto, I leverage everything, all the C++, all the good things in C++ are on the slide right here, right? All the good things. This is awesome. So I get like constant time. Which is your favorite? Please. Thank you, Mr. Baxter. The point was, considerations of performance. Like inline is not going to work out. Trivial destructors are not going to work out. A variety of things are not going to work out, right? So it's kind of nice to look at, pretty. But when you look at the performance, maybe it's not going to get you there at all. So it is constant time. It is small. It is simple. It is easy to understand. It doesn't have many template instantiations. We're going to discuss that in a minute. But GCC and Clang, and I assume Circle as well, because Bill mentioned, kind of raised the concern, they're not going to inline those indirect calls. So it turns out it's going to be way slower, unless maybe you have like, a couple of tens of thousands of types. In that case, maybe it's going to work, right? And also, it's like wasteful for trivial destructors, which it turns out it's often. Like you're going to have this indirect call to a function that does nothing, and then it returns having done nothing proudly. That's not the way to code for efficiency, right? So it turns out that this is not a very good solution, except in some cases when you have many types and many have non-trivial destructors. So it may be the case that this solution may be good in some instances. And we get to the true solution, which is called algorithm selection. Algorithm selection means I have a variety of algorithms at my disposal: linear search, binary search, constant time with disadvantages, yes? And then depending on my inputs, depending on the instantiation variant, how many types do I have in there? How many types have non-trivial destructors? How expensive are the destructors? Somehow, maybe you have a way to formalize that. So depending on all of these inputs, you may decide on which algorithm suits you best, right? Maybe linear search would be best for like up to 7 elements or 4 elements, right? Maybe you're good with, no problem. And then you do log search, and maybe if you have many types that all have non-trivial destruction, maybe you go with the constant time. So algorithm selection is kind of a great thing in a variety of situations in programming, including this. I want to select during compilation the best algorithm to use. That brings us to a qualitatively new challenge that we have. There's a new era dawning in C++. There's a new era, which is mixed mode algorithms, in which some things I need to do during compilation, some things I need to do during runtime. There is actually a field in computer science which is called partial evaluation, which actually deals with this for many years now. But in C++, it's a very peculiar form of partial evaluation. It's like you gotta do all of these algorithms that are mixed mode. You know, what do I know during compilation? What do I know at runtime, etc. So it turns out that there is a hidden disadvantage of that logarithmic binary search solution. It turns out it instantiates a quadratic number of templates. Let me show you why. You see, these ifs here are runtime. If, else, right? So destroy log is going to instantiate destroy logs on both branches, even though it uses only one. So that means if you look at the static preconditions, that's why I put it there. If you look at the static precondition, you're going to see that destroy log is going to be instantiated with all pairs of numbers that are, one is less than the other, between 0 and n. That's quadratic. So looking at a quadratic number of instantiations, it turns out if you don't pay mind to these actually may break your CI. Because your virtual machines in your CI system may not have enough RAM. And this is a problem that I am working on. Like, it's a real problem at a company. They're losing money because of this, right? So it's a real problem. So this is another qualitatively new issue that C++ programmers are going to look at in the times to come. Because right now, there's so much introspection going on and so much more introspection coming that all of these opportunities are going to arrive at us. We're going to start using them, and we're going to start paying the price. So, save these words. So please remember, I was the guy who said it. So remember, a new era is dawning when you're going to be very mindful about what you do during compilation versus runtime, how much memory you're taking to compile the program, and how much time you're taking to compile the program. So this is just the beginning, friends. To summarize. So to better understand type deduction and variadic functions, remember the rule of greedy matching and the rule of fair matching. Variant destruction is difficult. Get ready for these mixed mode algorithms. And please add type sequence to the C++ standard. Thank you very much. Thank you. That's one more beer for me right there. So I can take a couple of questions from here and online. Dave, please.
I don't know if this is a question, but more of an observation. When variadic templates came in, I saw a lot of work being done directly with parameter packs, and I thought, oh, this is a hopeful sign because we're going to get away from, creating these metafunction wrappers that cause a template instantiation just to analyze them. And now I see at the beginning of your talk, we need these class template components just so that we can deal with our parameter packs reasonably.
Awesome.
So, what's the real future? What's the
real future
for C++?
It's really awesome you mentioned that. One thing that comes clear with once you have type sequence and the three primitives that allow you to kind of create any data type, there's the cost of doing all these things are well known. So the Lisp has been doing it for like 60 years, right? So the cost of doing things like I want to reverse a list, I want to sort a list, I want to do all these things, Lisp has done them. So the complexity of these operations is known. When you operate directly with parameter packs, you always risk of doing something that looks cute, but you have no idea how many, it's quadratic or cubic. Or I've actually ran into a cubic algorithm once, I'm not kidding. So you can always run into these weird cases if you do kind of unwitting manipulation of packs directly. Yes, please.
Just a comment. I work at a team that has implemented its own variant, and just wanted to comment that the cascading of if-elses on the runtime linear search that you described earlier in the Clang family of compilers gets transformed into a jump into a table. So it is basically the same thing as lookup into an array. But not the GCC family or Visual Studio. Furthermore, when you use a table of function pointers, an array of function pointers, that is like an optimization barrier for all compilers. So sometimes it is better to use the linear search in Clang because it gets converted to an indirection with full optimization before and after this jump.
That's awesome. Thank you very much. I tried my best to get that constant time destructor optimized, and kind of LLVM kind of a little kind of in very few particular cases did something meaningful, but most of the time, no. Any other questions? All right, friends, I would like to thank you very much for being here today. Thank you. You're awesome. Thank you.